All right, let's get started. So, do you remember what we talked about last lecture? So we're going to follow our discussion on Griffith's analysis, right? So let me just remind you what we did very quickly. This is what we have last time. So remember, keep our the problem that we are trying to solve in mind. We have this issue of stress concentration around the floor, right? And what Inglis did is that he predicted a infinite stress at the crack tip. Now that is, to be pretty difficult to to digest and to accept that we have infinite stress at the crack tip, but that is explicitly appearing in the fracture strength result that he derived. We derived that stress concentration around the crack tip from Inglis, and we have that radius of curvature at the crack tip explicitly in the equation, right? So that depends on the sharpness of the crack. Now, and that's very difficult to use, because we never know the radius of curvature around the crack tip, right? That's very hard. How much do we, how do we measure that? Right? It can be atomically small. I mean, sometimes it can be microns, but we don't know, right? So that is one of the difficulties in English solution, and therefore that's where we started looking at at Griffith, or Griffith started looking at a problem, and try to get around that issue around the crack tip, and instead of using that, trying to directly calculate the stress of the crack tip, well. He used an energy balance approach, right? So, and that's where we were talking about last lecture, right? So he considered two plates, right? One without a crack, the other one with a crack. And the principle of thermodynamics tells us that these two configurations of the same solid, and if one configuration is preferred, then the preferred configuration must have a lower total free energy, right? That's what thermodynamics tells us. If the solid has a choice to choose, which configuration to go to, he will go to the lower energy. So that's why we were accounting for all the energies associated with each of these configuration. And so, well, the first energy that we need to account for is the surface energy, right? There's no surface energy here in the crack, in the plate without a crack, so that's 0. In here we have 2 additional surfaces, right? So, and each surface has a length of 2a and a width of b, or a depth of b for the plate, and therefore we get to this total energy difference between these two, right? So this is positive just because we are looking at this crack configuration with respect to the non-crack configuration, right? So with 2 surfaces, each has a dimension of 2a times b, right? And this is the surface energy gamma, right? And gamma has the unit of energy per unit area. So in the end of the day, this is in the unit of energy, right? That's the total energy. So this is the difference, right? This is not, we are not looking at the absolute energy of these 2 configurations. We're always looking at the difference, because to count the absolute energy of a certain material is always hard. We have to count all the surfaces that this material has, and so on. But if we count the difference, a lot of details are not needed. And so the second part of energy that we should be looking at is the work done, right? So there's a stress being applied on both configurations, and so the difference between the work done of these 2 configurations is exactly 0. Okay, again, we're talking about the difference, not the absolute work done. Now that's because we have fixed once we reach sigma stress of sigma, we fix the loading grips when we do not move. Right, so we do the same for these 2, right? So they undergo the same amount of displacement to reach sigma, and then we stop there for both of them, okay? and therefore there is no difference in the work done between the two configurations, and therefore it is 0. Now the last part is the elastic strain energy. That's where we started. The last part that we talked about, right? So because we are loading this material, right? So there's work done that is being applied to the solid, and therefore the solid itself accumulates some of that energy inside that piece of solid, and that's the elastic energy, right? So you get that in intermediate mechanics of materials or solid mechanics, right? So we can write down, for example, for a piece of linear elastic material, the string energy density is exactly 1/2 sigma times epsilon, right? Stress strain 1/2. So obviously we need to integrate over the whole body, right? Because we're accounting for the total energy. So for this one, it's really easy, right? And because there's just, there's no place, so there's, 1/2 times sigma square over E, or 1/2 sigma epsilon times the volume of the whole thing, right? That's just uniaxial tension. We can calculate easily. This one is difficult because to integrate, we need to know the stress distribution, because we need to integrate the stress field all around that the piece of solid, right? So what Griffith did is that he used the solution by Inglis. Okay, so Inglis computed, or he calculated the stress field for elliptical hole, right? So you're going to see that in your homework. What does stress field look like? But he calculated it by hand, and what Griffith did is he took that solution and integrated over the whole volume of the crack plate. Okay, and then if he subtract the two configurations, the strain energy, this is what he get, right? Sigma square over E pi A square B, right? This is the total energy of this configuration, the difference between these two configurations. Now, this is minus. That means that the energy in the second configuration, in the crack configuration, is lower than this one, right? And this is intuitively correct too, because we know that around the hole, we know that the stress is not, around the hole, some piece of the solid is not taking any stress. Okay, so there are we have less material here, so to speak. That less part of the plate is actually taking stress. So this is lower elastic energy. Okay, very good. That was the summary of what we did, and now what we need to do is the final step, right? So because we've counted all the energy we can think of about the system, right? The surface energy, work done, and elastic energy. So we want to then add them up, right? Because we're looking at the whole system as a thermodynamic system, so we count all the energy, and the total energy is the sum of all of them, right? So total energy difference. So I'm using U. This is, a notation that we often use for potential energy, or the free energy of an elastic system. So I just add all of them up, right? We have the surface energy difference, and I have, external work done is 0, so it's 0. I have the string energy difference. So that's simply this. So let's make a plot of this energy function as a function of the crack length, right? Just to understand the physical significance of this result, right? We are getting very close to Griffith energy balance. This is a very simple idea, but extremely insightful, extremely useful. So think about the components of this total energy. We have a linear function, positive, right, coming out from the surface energy difference, right? That is just a linear function with respect to A. Okay, so I'm plotting. I just need to sketch a linear line, and that is the surface energy component, right, for A, B, gamma. It's linear with respect to A, the crack length, and it's positive. The other one is the elastic energy, right? And in this case, this is a quadratic function, and it's negative. So we sketch the negative. So it's an upside down quadratic curve. Okay, something like that, right? This is sigma square E pi A square B. So now next, right, this is the individual components, and we add them up. We can again sketch the total energy, right? So this is, so without actually computing anything, we can, we are able to just, look at the shape of the curve, right? So obviously, we can put in numbers and see how this, exactly how these two curves interact, the magnitude of it. But, without doing that, we can already, by, physical insights and sketching these curves out, we understand the shape of the curve, which allows us to do a lot already, okay? Let me change to a different paper. So the total energy looks like this. So you see this side by side. So just, if you have it on your notes, you have a linear curve and a quadratic curve going down, you add them up, this is what it looks like, okay? So now we have to use some concepts in thermodynamics, or and also in Newton's law, right? So take a look at the shape of this curve. This curve has no minimum, okay? So this is the total potential energy or the free energy of the system. There's no minimum. This is going to keep going down. Okay, there is 0 at the beginning, right? That corresponds to, zero potential energy difference. Okay, and there is, the most striking, feature is this, right? At the peak of that, there's a peak in the free energy. And corresponding to that peak, there is going to be the floor size. I'm calling it A star. Okay. Now this A star has some physical significance. But first of all, let's discuss this plot. Now we are thinking about two copies of the plate, one with a crack, one without a crack. Okay. Now, the potential energy curve tells us something about it, right? Because we know that if a configuration is going to happen, right, it's going to appear in reality, it must have a lower energy, right? So let's, for example, consider two cases. The first case is that we have a crack that is larger than A star, right? So think about this, right? A is yet to be specified, right? This is a general variable. Let's say that I make a crack that is larger than A star. Okay, we're going to calculate what A star is, right? Exactly. So that means that I'm at this part of the curve, right? My crack plate has a crack length that is larger than these, right? So what is going to happen to that? To this plate, right? So this 2A is larger than 2A star. Okay, let's think about this. I know A star. I calculated it. I'm going to tell you how to calculate it in a moment. But let's just think about this situation for the moment. We have I make a plate with 2A which is larger than 2A star. So a crack larger than this number. So what's going to happen? Is the plate going to crack or not? According to this. I'm over here. My A is larger than A star. Okay? So if, and then you look at, a neighboring point, let's say here, right? I start with an A that is larger than A star. There is a configuration for the system to go to a lower potential energy, right? I'm here. I wouldn't go backward, right? Because to do that, I need more energy, right? And this is from a dynamical system. It wants to go to a lower energy level. So it's going to go this direction. And that means what? It's going to crack. It wants to increase in crack length because that gives the total potential energy or the free energy to be a smaller value. Yeah? So I have a stress applied, sigma. I have yet to specify. This is very general equations, right? And somehow, with all this analysis, I can tell you that if you have a crack length that is larger than this, it's going to crack. It's going to keep cracking. There's no minimum. It can, keep going down. It's not going to stop at some point. Right? So it's going to crack, and then it goes until you don't have a plate anymore. Right? So this is, case number one. That is when you have a crack length that is larger than this. So we call this the critical crack size, right? A star. A star is the critical crack size. And what we just consider is that my pre-existing crack length is A, and this is larger than the critical crack size. I'm going to have crack growth. Condition number one, crack growth. Or crack advancement. That's because this is a more preferred configuration. Now think about it. So this is the total energy. So what does that mean for? Let's take a little bit more discussion into this. I know the total energy comes from these two components, right? And at some point, A star is going to keep going downwards, right? That means that the increase in surface energy, right? Because if you want a crack to grow, you increase in surface energy, but you will decrease in elastic string energy. So there's a competition of the two energies, and therefore, at some point, once your crack length, passes this critical size, the decrease in energy is faster than the increase in surface energy, so the decrease wins, right? So the reduction in energy wins, so that it's preferred for the crack to keep going because now there's less and less elastic string energy in the material, right? So this is the thermodynamic or the energy implication of this. So you have a competition of two types of energy. Now the other case that we did not discuss, right? Now we should discuss the other case, which is very seldom discussed in fraction mechanics textbook, right? Because we are interested in only crack growth. But then if you take the other direction, that's also quite insightful. What happens, right? So when A is smaller than A star, I start with a plate that has a crack length so small, it's smaller than the critical crack size. And so I'm over here. So according to the same argument and the potential energy plot that we have here, what's going to happen? It should go in this direction, right? That means physically the crack should combine and heal and disappear to zero. But is that physical? Is that real? It's not real, right? If not, then everything is so amazing, right? The crack just heals by themselves, right? You make some material with some flaws, they are not breaking. If they're not breaking, they must be smaller than this crack size. So they must start healing. But we don't see that. Now, so there is a simplification in this process, right? In this energy argument, because for crack to heal or for crack to combine, so the breaking process and the healing process are very different, right? At the atomic scale. In the breaking process, you just need to, separate the atoms, right? But then in the healing process, it's very difficult because you put two, surface together, they're not atomically flat. Right? There are cracks and also all this, on the surfaces, if you look in the microscope, they are not cracks. So they are not actually in the vicinity of each other at the atomic scale. Right? So if they are, they will actually heal. Right? And that is happening, that is what happens in ceramic sintering, for example. So you have, if you mix ceramics, or if you heard about how to mix ceramics, you have these powders, ceramic particle, titanium oxide, aluminum oxide. They come in bottle of powders. You can buy it too. And what do? You mix it in some sort of solvent. Sometimes it's polymer, and then you heat it up at very high temperature, 1,000 degrees Celsius. Now these particles, they heat it up to such a high level, and in this solvent, so they are freely, they can interact with each other, and they start becoming a piece of solid, right? That's how you actually make ceramics, right? The small particles start, adhering to each other, right? So, if you think about that process, it's like a crack healing because, at the beginning you have two, these, particles that are not combined, but, after the process you combine. But then you need to reach certain conditions. For example, the first one is it needs to have enough, mobility for the two particles at atomic scale to do this process. Okay, so the analysis is not wrong, but then for the physical process to happen, there are more conditions, right? But then thermodynamics predict if the conditions are right, you're going to have it. You're going to get that process. Now you have crack healing, but then don't take too much. Yeah, don't say get out of this classroom and say, well, crack is going to start healing, right? So I'm going to get a bad timing, right? This is not true. Okay, so this is the two conditions, and we identify now the crack size, the critical crack size. Now let's try to calculate it, right? How do we calculate this critical crack size? Because this is important. If I have a material, I know the critical crack size. I know it will start to have some idea how to design my materials, right? I want to stay below the critical crack size. At least I'm not going to get crack healing. At least I'm not going to increase the crack length or have crack growth, right? So how do we calculate A star? Well, we have everything we need because this is the expression for the energy, which is 4 AB gamma minus sigma square E pi A square B, right? Just think about calculus, right? Now this is a stationary point of the potential energy, right? Because the slope there is 0. So what we need to do is just to differentiate and set it to 0, right? So okay, let's do that. That's a real quick and easy differentiation. What we want to calculate is du dA. We want to differentiate that expression with respect to the crack size. Okay. Now in this process, our stress is constant. Right? Just keep that in mind. We are not changing stress. We go to the stress and then we stop there. Right? So just differentiating that, you're going to get 4 B gamma and minus 2 sigma E pi A B. Right? And I want to set that to 0 because I'm looking for the stationary point. I know there's only one, right? Just from, adding a linear curve with a quadratic curve, I know there's going to be only one point. Where the slope is 0, right? So that gives me the critical crack size to be 2 gamma E pi sigma squared. So this is, again, let's take a look at this, right? So we can calculate the A star given the conditions of the experiment that we are doing, okay? Because over here, elastic modulus and the surface energy, they are material properties, right? So if you take a piece of material, you know these numbers. You look it up in tables, you know these numbers. Now, stress is what is being applied. So if you know what you're applying, a certain amount of stress, and you want to know whether this is going to crack, then what you're going to find is what you want to calculate is, well, let's calculate what is the critical crack size for a certain amount of stress, and I just make sure that the crack size is smaller than that A star. Now, obviously, stress can be changing, right? So another way of looking at this equation or formula is to think about things in reverse, because there are two variables here, right? Sigma and A, they are varying in many situations, right? We can apply different stresses, we can have cracks that are different sizes, but E and gamma, they are constants, material properties, right? So if you turn this equation around, the other way of looking at this is actually looking at the strength, the fracture strength of the piece of solid. And that is the strength that is the fracture strength predicted by Griffith analysis. Okay? So if you remember, we've calculated several different fracture strengths so far, right? We started with the first one, that is the strength at the atomic level, right? There's a strength that we calculate from just by looking at atomic plane separation. Okay. Now the second fracture strength is based on the analysis at the stress at the crack tip, right? That is analysis by Inglis. He and again got a different value for the critical for the fracture strength, and this is Griffith. Okay, so we're going to make some comparisons very soon. But then, we'll talk about how they differ and what are the similarities. But before that, this is not where Griffith stopped, because this is all of them are theoretical analysis. So what you want to do, or what he did, is to prove it, right? So how do we prove it? The only way we prove something in science is to do experiments. So you need to think about experiments that are easy to do, practical, that we are able to do, but then at the same time validate this result. Okay, so what kind of experiments can we do to confirm the findings? Right. This is what the analysis tell me. I just want to know if this is true. So I need to think about experiments to do. So Yeah, Griffith is brilliant. Okay, it's brilliant. Very clear. Very clear thinker. Yeah, I don't know if we have, we have a lot more Ph.D. these days than in the time of Griffith, but I don't think we have that many clear thinker at that time. So what do we need to prove is, we need to be very clear about, what we want to prove, right? This is the equation that he derived. And think about this. There are two variables that can be changing, right? That is sigma and A, right? I take a piece of material, the loading is changing, can be changed. I can change it by loading it more and less. There's the crack size. That is something I can control. Okay, I'll tell you how he controlled it. What is not going to change is elastic modulus and surface energy of the material, right? You give me the piece of material, I cannot change these two things, right? This is a material properties. They give me concrete, I can't, make elastic modulus different. So, in other words, what he needs to show first of all, right, is that by rearranging this equation slightly, right, is that first objective confirm sigma A square root is constant. So that's the first experiment, or the objective of the first experiment, right? So why this very insightful, right? So the first time I looked at it, I didn't appreciate it, but now I appreciate it very much because it doesn't matter. So there are two parts of it, right? Because only these the sigma and square root A. If I put the square root A over here, the right hand side is constant. Okay. So they must be constant. Okay, sure. Well, yeah, that's obvious. But why does it have? Why do we not just directly prove they are equal to the exactly 2 gamma E over pi? Now that's where the subtlety here, right? Because you have gamma and E, they are gamma for example is extremely difficult to measure. Okay, for a solid, it's a surface energy, right? For a fluid, that's easy. Now, elastic modulus is relatively easy to measure, right? At that time, he could measure it. But gamma, you have a lot of experimental uncertainties, right? So, but if I can just prove that they are constant, I have not proved the full formula is true, but I already proved 90% of the formula is true, because the sigma and the sigma square root A equal some constant, this relation is true, right? That constant, I may not get it correct. Griffith may not be able to get it correct, but at least the relation, this is still true. Doesn't matter if I measure the gamma wrongly, incorrectly. If I can make sure this is just some constant, I don't know what it is, then this relation is already very, very powerful. Because I know I have proved one thing is that sigma varies with some constant and to the crack length square root. Okay, so the fracture strength varies quantitatively with the square root of the crack length. So this is part one. Obviously, part two is to make sure is to prove that constant is indeed so let's say C and C is indeed 2 gamma E pi square root. Okay, so this is the two experiments that he set out to do, right? So let's think about the first one, right? The first objective, Right, let's go through the flow process because that's more important than knowing the result. Right, let's try to follow his thought. So how would we do it if we want to prove this sigma square root A must be constant? This is brilliant experiment. Very simple. Everything that are practical and can be done with simple experimental setup, but prove something that is very, very useful. Okay, this picture here. So remember what sigma is. Sigma is the fracture strength, right? A square root. A is the crack length, right? So we again, let me remind you, this is the picture we're looking at. So what I need to do is I'm going to create several pieces of a glass plate. He used glass because that's linear elastic, very brittle. And he put cracks. He made cracks intentionally on each of these plates, right? So, and then he made these cracks so large that it's larger than all the naturally occurring flaws inside the solid. So if there is going to break, it must, if any cracks is going to advance, it must advance from this one because this is the largest. So, and he can measure it because he created that crack inside the plate, right? So even though there's all these micro flaws there, they don't matter because this must be the one that is going to start cracking first. So he vary A, right? So he can vary A because I can measure it, pretty precisely. Maybe I make 5 of this plate, 5 different crack lengths. And correspondingly, he measured the fracture strength, right? At what point the plate cracks through the crack goes through the whole plate. And I note down that fracture strength, right? So that's sigma and square root A. So he just have to compute this quantity from each of these 5 different tests, and make sure they are the same value, right? So it doesn't have to, the first objective, is not. I don't care what that value is, as long as they are constant. I already proved the first point, that sigma indeed varies with square root of A. That is already true. Now the second part is more difficult, as we talked about. Now I even further I want to prove that exactly how they are related, right? So I'm missing that constant. What does that constant relate to other physical properties that I can measure, right? Because if I only get this first objective, that's kind of limited use because I change to a different material, the constant changes. Even though I know the relation still holds, but what is the constant? The constant is change. Now, I want to relate that constant to some properties of that material, and that is the second objective. And how do we do that? Right? We need to prove that relation, and that is quite quite direct again. Right? What we need to do is to measure E and gamma. So E again, I said that it's not difficult to do with elastic modulus. Right? We do that pretty much by loading it and then measuring the change in length. Now gamma is the painful part, right? The gamma is the surface energy. So I don't know if you remember what surface energy means, and how do we calculate it, right? So we briefly talked about it in the context of at the atomic calculation, but that was a little bit abstract. So let's take a bit of a more physical approach, because now we need to measure it. We can't go to the atomic scale to measure things. We don't have that technology, not even today, right? So surface energy. So let's think about liquid, right? That's where things are easier to be explained because we had experience pulling out soap film, right? As a kid, at some point. So what do you notice from pulling out a soap film? What is the most annoying thing of that kind of experiment or activity? It's really hard because the soap film breaks. It's hard to control. You want to pull out a soap film. You have a kind of frame, right? You dip some soap, and you start to stretch out a film. If you can stretch it out as large as possible, that's really cool. But then it's very difficult because at some point it breaks. Okay, so that is a perfect experiment to measure surface energy, right? So liquid film. So the frame is this. I have a frame, some dimension, small b. There's a distance x, and there's a handle on that side, and that's the soap film in between. And I'm trying to put it with some force F, right? Think about the process because at the beginning we start with the handle close to one edge, right? So there's less area. As we pull the handle to this side and keep pulling, the area of the soap film increases. So the surface area increases, there's more surface, and the surface energy goes up, right? So there's there's surface energy change. Now, surface energy change must correspond to the increase in area. Okay, so what is the increase in area? So I can do that very easily, right? So let's say that this is the original position I have. I start with this position, and I start pulling it slightly to the right, and that in that process, that's the new configuration. Sorry, a new position of the handle, and there's a change in length. There's delta x. So the increase in area is simply 2b delta x, right? Because there is again two surfaces, top and bottom, right? So I'm drawing a 2D picture, but a film is still a three-dimensional film, right? Even though it's very small, it is a three-dimensional object, and then there's two surfaces. And there's increase, so the increase is this part, right? So there's delta x times b. There's increase. So the surface energy increase, and it's quite simple. It's simply the increase in area, again, times the surface energy of the film, right? Again, this is a material constant, right? Again, it's different for different materials, right? For soft film is so and so. For other liquid is different. So now we want to find out what this is and how we want to. The way we want to find it is again by energy balance, right? So to increase that energy, the surface energy, or that soap film from here to here there, I actually did some work to it, right? I have a force F, and then I increase in distance. There's a work done. And now in thermodynamics, when we say that there's work done to something, the convention is that this is a minus sign, okay? The work done to a system, you put a negative sign in front of it, because that is the energy that is not part of the energy of the system before, right? Of the soft film. So you put that energy into it. Now I can write down then again the same thing, the potential energy or the free energy of the whole system, right? Now when I say the system means what? Means the liquid film plus the applied force. Okay, it's not just the energy of the film, right? So from a dynamic system, sometimes it's not very intuitive, because we first of all have to think about the system. The system always includes the force being applied. And the change in that potential energy then is the increase to be delta x gamma minus f delta x, right? So that's all the energies that happen, that changes in this process, nothing else, right? So there's no elastic energy. This is a liquid, okay? So we don't talk about it. It's not storing energy, right? So what we need to do is just keep going with that calculation, right? So now du dx, I can just put the dx over on that side. 2 gamma b minus f. I want to differentiate that because when the derivative of the potential energy is at equilibrium. If the system is in equilibrium, that means that there's no more movement. I put a force there. The liquid film goes from here to there, and then I stop. The film stays there. Everything is in force equilibrium. And in force equilibrium happens at the same time the potential energy must be, the derivative of the potential energy is 0. Okay? So this is. So I hope you remember that from intermediate mechanics of materials. Okay? So whenever potential energy is 0, that means that now the body is in equilibrium. There's no acceleration and no momentum anymore. Okay, so now then this gives us a very simple relation to find out what's the surface energy, because I measure the force F, right, as long as the film does not break and is in equilibrium, then I calculate the surface energy. Then I can calculate the surface energy of the film. Okay? So you see that why it always breaks. It's very hard to control, because if there's only one surface energy, there's only one force you applied, the whole thing is going to be in equilibrium. If you slightly increase that force, right, let's say that you jerk your hand, okay, a slightly higher force is being applied. Surface energy does not increase because that's material. I mean, that's the property of the film. What you're going to do is that, you actually break the film. Yeah, because of course, because the surface energy is this much, and when you apply more than that, right? So you have to always at the equilibrium. You maintain the force at the equilibrium force while quasi-statically stretching it without increasing the force. Then you can stretch out, but then you have to be very steady, because a slight increase in the force is going to break the film, right? So that excellent, right? That's an excellent experiment. Very simple. Now think about the solid, right? This is liquid. Now Griffith wanted to measure the glass. It's a solid, right? It does not flow. How do you pull out the glass? It's tough. Eventually, he could do that by heating the glass at high temperatures, right? So what you need to do is to do the same thing, but solid only they don't flow at room temperature, but they start to flow when you heat it up. All the glass blowing. That's that principle, right? It starts become like a fluid once you heat it up. So what you do is you heat it up. You simply similar experiment, not a film usually, right? But that's very difficult for a solid. But you can pull out, for example, a cylindrical glass fiber, heat it up, and you start pulling it down. Assuming that the whole process is cylindrical, or you can measure the geometry, then you can keep track of the surface energy or the surface area change, and then you calculate the surface energy increase, and then you have a weight hanging down, that is the force. You maintain the force constant by putting a constant weight there, right? You don't. So there's gravity force, just here holding it, once it stops moving, that's an equilibrium. Every ring stops. Surface energy is balanced completely by the force, the weight force of the load you put on. At that point, you mark down that is the force, and that is the surface energy of the glass. Okay, so that's the glass. But then heating up the glass and then doing that experiment was not easy at that time. It's also not very easy now. Okay, so because you heat up to kind of 800 degrees and everything gets complicated when you're at high temperature. So the agreement was not very good. So it's close, same order of magnitude, but maybe 50% off. Okay, so we not to diminish any of that contribution. It's still a great experiment. Great work. So this is how he how he proved it. The second point. So I would say that the agreement was pretty good. Given all the limitations we had at that time. Now that's all good. Let's try to come back to the point I made earlier about all the different fracture strength and make some conclusions from there, right? So now we've done quite a few derivations, and now we have know a bit more about fracture strength than before. So, but let's recap all of that. Now, the first one is the cohesive strength. Let's discuss a little bit about the nature of fracture strength, because that's the point. There's this the concept that we've been using all the time before the time of Griffith, and we use it. And even though we know there are some fundamental flaws to it, because we did not care about flaw size at that point, right? The first classical fracture strength, I'm going to call it sigma C. Now, sigma C means the cohesive strength. From atomistic calculation or estimation, is this, right? E gamma over x naught, right? That is maybe the second lecture, and that just come from so x naught is the equilibrium distance, and we have the fracture strength from Inglis. Okay, so he calculated the stress concentration around the floor, and he said that, or he derived that a slightly different formula has a little additional parameters in there. Right, so you can, this is what we got last lecture, I think. So we have the A now, that is the crack length, right, that did not appear before. But we have now, because we know the flow matters, we have the rho, which is the radius of curvature of the crack tip. Is a difficult parameter to characterize. Nonetheless, he derived it. We still have the x naught. It's a parameter that we can calculate, right, just from atomic spacing, right? But there's a simplified version of this, because if we are looking at very sharp crack, then rho and x naught are about the same, okay, for atomically sharp. The radius of curvature around the crack tip is atomically sharp, is same as the atomic dimension, and so an approximation, more practical approximation can be made. That only depends on the crack size. Now that's Griffith. Now that's today. What do we have? I've had sigma. That's the fracture strength. Let's put an F here just to indicate. That's the fracture strength. That's 2E gamma pi A. Okay. So let's take a look at these. Let's compare these two. principally there are some similarities and differences here, right? What is the similarity? Well, the similarity is that they both have the crack length A in there. Okay, so that's the floor size dependence that appear in both of them. Obviously because they both recognize it must be there. What is important is that they both predicted sigma varies with 1 over square root A. Okay, they both have that relation, and then you multiply by some constant, right? Additionally, English has a sensitivity to the radius of curvature, right? And that is not appearing in Griffith. Okay, so that's why we said Griffith bypassed it, right? But we're going to come back to to the reason why this does not appear here, even though Griffith used English solution. So it's amazing that how somehow it did not appear. So we're going to understand this a bit more later. But then the constant is going to be slightly different, right? So I have this has 2 over pi, and over here this is just 1 over 2, right? Square root of 1 over 4, right? So slightly different constants, but then the E and gamma, which is the surface energy, are both there, right? So there are some similarities. And it turns out they are both, in the same order of magnitude than the experimental strength. Okay, they're much closer to the experimental strength measured. Right, this one does not. Right, so closer to experimental strength. Experimentally measured strength. Okay, so I have 15 minutes left. I'm going to start the next topic a little bit, and then we're going to finish off next lecture. Now, this is all good. Now, Griffith got to this point, and he measured glass, which is a brittle material, linear elastic, and this worked, with acceptable accuracy. So everybody was happy. But then the problem came later. Because at that point we are looking at Liberty ships. Okay, that's one of the problem that. So this existed, right? This is 1921, I think, right? If I don't remember correctly, yeah, 1921, and this is coming out, and we have the Liberty ships problem. That is World War II, and then these Liberty ships, they are steel, right? So at that point we have steel construction, and so what happened afterwards is whether we can apply this sort of analysis of Griffith to fracture of steel, because that is the practical problem on hand that we were not able to capture with classical strength theory. So, and the short answer is, at the initial application of that did not give any good results. Okay, so. So let me go back here. Okay, good. So the problem is, at that point now, there's two figures that were very important. There's George Rankine Irwin that I mentioned in the first lecture, and also oral one. I did not mention that, but he was also one of the figures that dealt with this problem. We want to apply that to fracture and see, steel, and see if that Griffith analysis is correct. So that's what he did. Again, we repeat that experiment of Griffith on steel. Take a steel plate, make some cracks, different lengths, measure the fracture strength, and so again, you want to verify again whether Griffith analysis is correct. So again, follow the same thought, two parts. First one, still proved to be correct. Okay, sigma and a square root of a still constant for steel. This is good, right? So the fundamental physics is captured. The second part, no good at all, right? That constant predicted by Griffith, which is gamma e square root over pi, is not the same. What is being measured is much larger than that expression. Okay, so that is the reason. So that is the pain point of this analysis. And so again, what is the issue of that, right? So think about this now. Brittle fracture, and think about steel. Steel is not a brittle material. Okay, and one of the most distinguishing feature of a ductile material compared to brittle material is the amount of plasticity happening in the material. In brittle materials, there's almost none, no plasticity, plastic deformation before cracking, but in steel there is. Okay, so now think about this constant and surface area, the surface energy. Again, where could be the problem, right? So if we think about this expression here, now 2 and pi, they are just constants. Elastic modulus, right? We can pretty much get that well, so that not suspicious. The issue is the gamma. Okay, so gamma, think about it, is the energy needed to increase the surface. So that means a breaking. You need to break separate planes, separate atomic planes to increase the surface energy. And that energy is the energy that is stopping you from cracking, right? The only thing that is on the material is that surface energy that's stopping you from cracking it. You apply some force, that surface energy is the one that is resisting it. So, however, in steel, there is one more thing that is happening, because you have experience just pulling some plastic back, right? It does not crack for a long period of time until you load it, extremely extended period of time and extended length, and then it starts maybe cracking. Start with a small hole and then start cracking, right? So there's a lot of energy spent on plastic deformation, right? So plastic dissipation is another mechanism in ductile material that would consume energy. Okay, so you have one more thing that is preventing you from cracking, and that is shown in this picture. So this is a picture that we have in on a microscopic scale around the crack tip, right? At the crack tip where you have stresses, very high stresses, you're going to develop a plastic yielding zone. Okay. So this is a picture of the crack tip. It's a schematic picture only, right? And the shape of the plastic deformation zone is like a number 8. Okay, so you're going to again later on do a finite element analysis to just verify and visualize that. But this again is analytically derived back in the days without finite element. So people are very good. The mathematics were very good, and then they predicted that is a figure 8 shape that is plastic deformation. So because we know that at the crack tip that's where the stress is highest, right? That must be the location where the plastic deformation starts to happen, and that looks like that. Now, that plastic deformation consumes energy. So as your crack advances, that zone moves with your crack. So you have fresh material inside your plate that has not plastically deformed. As your crack advances, it always meets new, fresh, elastic material that has not plastically deformed. So that mechanism is always there as the crack grows. It's getting into new area, and that gives some plastic deformation. And so all the way that as the crack grows, you consume energy. So there's two components of that energy dissipation. So this is a modified Griffith criterion that is proposed by Irwin and Orwell. Okay, so the modification is quite simple, right? I know there's surface energy that is associated with actually breaking the surface, but before I actually break the surface, there's also energy going into plastic deformation. So I just need to calculate. I just need to account for both of these. So the final result modification that we need is to okay. I don't have it here. Okay. Let's go back here. So let me back off a little bit just to maybe explain that process again of fracture in steel. I think it's so that you get a more a better impression of what's going on, right? Instead of just a verbal description. So we have a plastic zone, some stress being applied, just making half of the crack, okay, just to save me some time. So that's the plastic zone. So you increase the stress, and now the crack starts to advance. So now it's slightly longer, the crack length slightly longer. But then the plastic zone, so originally is around here, okay? A different stress, higher stress, sigma 2. So I hope you can understand this picture, right? Because at the beginning, this is the pre-crackling. The crack already exists in the steel. I put stress on. It starts plastic deforming at the tip, and I increase the stress. The energy is enough to make the crack advance, so it advances. Let's say that to this position. Now, because this is the original position, so all this path that the crack tip has crossed is all plastically deformed. Okay, so that zone now extends to here. That is the front of the crack, and this position, and this is the current front of the crack. But these are all already plastic deformed because the crack just passed through it, so it left behind that plastic zone because it's permanent, right? Plastic deformation is permanent, so it stayed there. This is the situation I was talking about. Now, so we distinguish for brittle solids or brittle fracture. The only resistance to fracture is surface energy, so 2 gamma, right? Whenever you make a crack advance, there are 2 new fresh surfaces created, and gamma is energy per unit area, so it's 2 gamma, okay? But for metals or for ductile materials like steel, the surface energy, the resistance to fracture has one more component, which is WP, the plastic work, the energy dissipated because of plastic deformation. And this is due to Irwin and Irwin. So they modified Griffith criterion by simply changing the surface energy to surface energy plus the plastic work. So the modify Griffith. Everything stays the same, but instead of okay, so E2 gamma okay, that's the only modification. Okay. So just one last word. So there are some more. We're going to discuss these terms. The surface energy, the plastic dissipation work, right? So I mean, all these things, are useful only if we are able to actually calculate and measure them. Okay, in reality. And so, but one thing, just one last point to make is, think about the fracture strength. The fracture strength is not a material property. Okay, right? So by now we should know that because it varies with samples and it varies with crack size. So it's not a fracture. So it's not a material property like elastic modulus, right? You give me a material, it must have the same value. So it's incredibly difficult to use, and therefore we don't like to use it. But then, what is a good concept or parameter to use to understand which one, two pieces of solid, which one has a higher, or two pieces of materials, which one has a higher fracture resistance. Okay, then this is incredibly useful because now it will tell me, okay, is plastic is still more fracture resistant than concrete, or is plastic more fracture resistant than rubber? So we want to answer these questions because then we understand it and we want to pick the right material for whatever we are doing. And so there is a concept that we want to be independent of crack size and independent, and it's actually truly a material property. And this is something we're going to call it fracture energy, and that's what we're going to talk about next lecture. Based on this result we have today. So I'll see you next week.